introduction for the magnetic effects of electric current. A charge at rest produces an electric field only. This we have studied in our very first lesson of electricity, electrostatics. A charge in motion produces both electric and magnetic fields. A charge at rest could produce only electric field, but a free charge in motion, not in a conductor, a free charge in motion could produce both electric and magnetic fields around it. But a current carrying conductor produces only magnetic field around it, no electric field due to a current carrying conductor, since a current carrying conductor is electrically neutral. When a conductor is carrying current, even though the electrons are flowing through this conductor, as a whole the conductor is electrically neutral. So there is no electric field due to a current carrying conductor. Only magnetic field is possible around a current carrying conductor, and that was confirmed by Oersted by a simple accidental experimental discovery it is. So Oersted found that a magnetic field is established around a current carrying conductor. And now let me study various phenomenon and various parameters with the magnetic field due to a current carrying conductor, and it is determined by different laws, Amperes, like Amperes Law, Biot Savart's law, etc. So we study. Now let us study Amperes Law and Biot Savart's law. So first let's take up Amperes Law. The line integral of the magnetic field induction about any closed loop around a system of current carrying conductors is equal to the product of the permeability of the medium and the net current enclosed by the curve. The statement of Amperes law says that, more elaborately called the Ampere circuital law, it is the line integral of the magnetic field induction about any closed loop around a system of current carrying conductors is equal to the product of the permeability of the medium and the net current enclosed by the curve. The mathematical form of the Ampere circuital law is the line integral of B bar dot dl bar over a closed contour, over a closed path, is equal to mu naught times of the net current enclosed by that loop. Here is the integral of B bar dot dl bar over a closed contour, closed loop, is equal to mu naught into sigma I. In calculating the net current, the algebraic sum of the currents is to be considered, taking in reference to the plane about which the loop is considered, taken outward currents are positive and inward currents are taken negative. Around the system of current carrying conductors, we are going to take a closed loop, and the closed loop reference plane, if you consider, in respect of that reference plane, the outward currents are taken positive and inward currents are taken negative. And any current outside the closed area is not included in the net current. Only those currents which are bounded by our referred closed loop are to be taken in calculation of the net current. The Amperes law is analogous to the Gauss law, what we have studied in our electrostatics. That is, integral of E bar dot ds bar over a closed loop is equal to 1 by epsilon naught times of the net charge enclosed. This we have done in our electrostatics Gauss law. And here the Amperes law is just analogous to Gauss law in electrostatics. And the Amperes law is useful only when the closed path is symmetric with known limits. In Gauss law also we have studied that. The closed loop is to be selected in such a way it is symmetric with known limits. Here also we have to apply a limits law. That's why for linear conductors where the closed loop about which will be a concentric circle with the limits can be known now 0 to 2 pi r, where r is the radius of that circular loop we choose. So such symmetric closed paths with the known limits have to be selected so that the Amperes law application becomes convenient to us. So Amperes law is useful with that limitation only when the closed path is symmetric with known limits. So we have some numericals on this concept and we take up those numericals in our numericals video. And then let's understand the Biot Savart's law. This is more useful for us to find out or to determine the magnetic field induction at a point in the field due to a current carrying conductor. This time it need not be a linear conductor. It can be now any conductor we can choose, a current carrying conductor, and we can calculate the magnetic field induction at a point in the field due to the conductor at any point. And now to understand the magnetic field induction at a point, let's first understand what is meant by current element in reference to a current carrying conductor. The product of the current and the length of an infinitesimal small segment of the current carrying conductor is called current element. The product of the current value I and the length of an infinitesimal segment of the current carrying conductor is called the current element. If here as shown in the figure, dl bar is a small segment of the conductor, then the current element is I into dl bar. It is a vector in the direction of the current in that infinitesimal segment of the conductor. So I dl bar is a current element. Now to find the magnetic field induction at a point P with a position vector r bar from the current element, this is the point P referred at a position vector r bar from the current element. Now the magnetic field induction at that point due to that current element denoted by dB bar is such that dB bar equal to mu naught by 4 pi I dl bar, this is current element, cross r bar whole divided by r cube. This is the form of Biot Savart's law. The magnetic field induction at a point P with the position vector r bar from the given current element is such that dB bar equal to mu naught by 4 pi into I dl bar cross r bar whole divided by r cube, where mu naught stands for absolute permeability of free space having the value 4 pi into 10 power minus 7 Tesla per ampere meter or Henry per meter, simply we say. So dB bar stands for the magnetic field induction at the point P due to the current element. And further, if we expand this context, the direction of magnetic field, that is dB bar, is that of I dl bar cross r bar. Here this is a vector, the cross product vector of I dl bar and r bar. So if I dl bar and r bar are taken in one plane, and the direction of dB bar can be found by using right hand thumb rule, and it is perpendicular to both the current element I dl bar and the position vector r bar. The right hand thumb rule is, if you hold the conductor, here the conductor element in your right hand, so that the thumb represents the direction of current through it. Then the wrap of the 4 curled fingers which grips in the conductor indicates the sense of direction of dB bar at the point. And now the magnitude of dB bar equal to, here the magnitude of the vector, mu naught by 4 pi I into magnitude of dl bar cross r bar divided by r cube. Here dl bar cross r bar magnitude is dl into r into sine theta. Here where theta is angle between the idl bar vector and r bar. Here is the angle as shown, theta. So now in this r, the expansion of dl into r into sine theta we get divided by r cube. When r gets cancelled, so the formula is modified as for getting the magnitude of the magnetic field induction at the referred point as mu naught by 4 pi I dl sine theta divided by r square. If we want to find the magnetic field induction at the point P due to the total conductor with the length limits say 0 to L, here it is given only due to the current element dB bar. If you want due to the total conductor with the length limits some 0 to L, suppose we take the in one of our applications, the conductor is a circle and our referred point is center. And now on this circular current carrying conductor, we take a small element dl bar, and due to that current element I dl bar, we find out the field induction at the center. And if we were to apply the limits of the conductor are going to be 0 to 2 pi r. Here in this case, general case, the limits are 0 to L. So we can easily apply this rule for finding out magnetic field induction at the center of a current carrying circular loop. By limits 0 to 2 pi r for the conductor. Here 0 to L, general rule, integral of dV bar under the limits 0 to L is equal to mu naught by 4 pi integral of I dl bar cross r bar by r cube under limits 0 to L. Here by taking the scalar, then also we can apply the same now, limits we can apply. And Biot Savart's law is an inverse square law and is the magnetic analog of Coulomb's inverse square law. Here you see B bar is, of course here r cube is appearing in the denominator, but in the scalar form you are finding now the inversely proportionality for r square. So here in the expansion of this expression, only in the denominator r square remains. So Biot Savart's law is an inverse square law and is the magnetic analog of Coulomb's inverse square law. Earlier the Amperes law is analog as to the Gauss law as we understand.